Hello, welcome to SPMM Revision on Demand. In this podcast, I will discuss the topic of meta-analysis. Let us first consider the two major types of research studies. Research studies can be classified into primary research and secondary research. In primary research, the data is collected from individual subjects. Example, in an RCT comparing olanzapine and fluoxetine for depression, we will collect HAM-D scores from individual patients who underwent this trial. In secondary research, the data is collected from the studies that are already completed. A person who conducts a secondary research does not have to interview individual patients to collect data for his or her analysis. Examples of secondary research include narrative reviews and systematic reviews. Let's now see the differences between these two types of reviews. For a systematic review, the reviewer has to assemble previously completed studies in a systematic fashion. Usually, a protocol is initially prepared to define how to go about collecting the previous studies, with inclusion and exclusion criteria for individual studies, measures in place to reduce publication bias. Such systematic reviews are often accompanied by meta-analysis. On the other hand, for a narrative review, an expert synthesizes the results of previously completed studies collected in an unsystematized fashion. In other words, the expert assembles the studies that he or she knows are important or interesting for the topic of interest. What is a meta-analysis? A meta-analysis is nothing but a numerical synthesis of results compiled from individual studies to produce a pooled result. Why is a meta-analysis desirable? By pooling a number of smaller studies, we are now generating more ability to find an effect if the effect truly exists. In other words, due to the large sample size that results from pooling all observations, we are able to increase the power of our search. We can do a meta-analysis even with 2 studies, but more the number, the better the study becomes. We can conduct a meta-analysis on any type of primary research, but randomized controlled trials are the most frequently meta-analyzed type of studies. We can discuss several aspects of a meta-analysis by considering the anatomy of a forest plot in detail. This is a forest plot reporting the results of a meta-analysis of studies that compare an active intervention with placebo. You can see that there are 3 studies that are combined here in this meta-analysis. Each study is represented by a black square box with a horizontal line passing through the box. The location of the square points to the point estimate value, that is, the effect size or relative risk value reported in the corresponding study. In this case, you can see that study A reports a relative risk of around 0.5, halfway between 0.1 and 1. The horizontal lines represent the confidence intervals around the point estimate of each study. For trial A, you can see that this corresponds to values 0.05 and 5.49 as shown in the accompanying text. The diamond lozenge represents the pooled result obtained using the meta-analysis. The edges of the lozenge indicate the confidence intervals around the pooled estimate. The results of the pooled results are more precise than the individual studies, so the confidence intervals will generally be in a narrow range for the pooled results. From the p-value of the pooled result, you can see that there is no significant difference between the placebo and the active intervention. In fact, you can immediately assess this by looking at the line of no effect. This line passes through the lozenge. This means that the pooled result suggests that there is no significant difference between the 2 arms. If you look more closely, you will see that this line cuts through the horizontal lines of every trial in this meta-analysis. So, none of the individual studies reported a significant result in the first place. Combining them did not reveal a significant result either. If the diamond lozenge falls cleanly on one or the other side of the line of no effect, we can assess the scale of the treatment effect. In this example, right side of the line of no effect indicates a result favoring placebo, while the left side represents a result favoring the active intervention. As there is more power, can we always trust the results of a meta-analysis? The quality of a meta-analysis depends on various factors. Higher the number of included studies, larger the sample size of individual studies, better the quality of individual studies, and more similar the methodology of individual studies, better the quality of the meta-analysis. If we combine a small number of mostly poorly conducted studies with small sample sizes, the results of the meta-analysis will remain questionable. In other words, if we put garbage in, we will get garbage out of the meta-analysis. The term often used in the context of meta-analysis is weighting. As the name suggests, weighting refers to the influence attached to each study when computing the pooled estimate. Weight is represented by a number with no units. Weight assigned to individual studies is usually based on the following characteristics of individual studies. Studies with large samples get larger weight. Studies that report more precise results, that is, studies with a narrow confidence intervals around the point estimate, get larger weight. In some cases, studies with more generalizable or pragmatic results may get larger weight. Studies conducted using a more robust, unbiased method often get more weight than poor quality studies. The researchers conducting the meta-analysis decide which of the above four factors will be given importance when assigning weights. So just to recap, so far we have seen the concept of meta-analysis within the context of secondary research, and we also looked at the anatomy of a forest plot, especially focusing on the black square boxes and the diamond lozenge, and we've also looked at the concept of weighting. Let's go back to this forest plot again. You can see the weights assigned to each study is listed here. Out of the total 100% weight, a large portion, that is 77.7%, is assigned to study B, which has the most precise results. Okay, now moving on to another term that you will often see in the context of a meta-analysis, that is heterogeneity. In a systematic review, if individual studies are conducted with similar methodology, this allows meaningful combination and synthesis for a meta-analysis. Just like peaches and nectarines, individual studies are often similar but not identical. The differences among individual studies is termed as heterogeneity. Heterogeneity may be clinical, methodological, or statistical. The term clinical heterogeneity refers to differences that occur due to clinical variations in trials. Between trials, the samples may be very different. For example, trial A may be a double-blind RCT comparing fluoxetine with placebo in severe melancholic depression. Trial B may be comparing the same interventions, fluoxetine and placebo, in the same design, that is a double-blind RCT, but the sample may only have moderate or mild depression. Such differences can also arise due to variations in diagnostic practices, differences in disease severity, and variability in healthcare settings. Clinical heterogeneity is describable but not measurable. Moving on to the term methodological heterogeneity, this refers to heterogeneity resulting from differences in study methodology. For example, trial A may be a double-blind RCT comparing fluoxetine with placebo in severe depression for 6 weeks. Trial B may be comparing the same interventions in a very similar clinical sample with severe depression using the same double-blind RCT design but for 9 weeks instead of 6 weeks. Methodological heterogeneity is describable but does not need numerical quantification. The heterogeneity that requires numerical quantification is statistical heterogeneity. Statistical heterogeneity arises because individual trial results are not always consistent with each other. While some show a benefit with active intervention, others may show benefits with placebo. Look at this forest plot. You can see how the individual study results are not the same. No two studies report the same point estimate values. These vary so widely that these are falling on either side of the line of no effect. Statistical heterogeneity is describable and measurable. This is the most important type of heterogeneity when it comes to the procedure of meta-analysis. Hereafter, if I say heterogeneity, I mean statistical heterogeneity. The presence of statistical heterogeneity affects the mathematical method that can be used to arrive at the pooled summary results in a meta-analysis. If there is a significant statistical heterogeneity, we need to use random effects model to arrive at the pooled result represented by the diamond lozenge. If there is no significant statistical heterogeneity, then we can use fixed effects model. So, what is a fixed effect analysis? If there is no significant heterogeneity, we can assume that all the studies share the same common treatment effect. That is, they are somewhat homogeneous. We can ignore between study variations and assume that the effect is fixed and does not vary between studies. So this can be applied only if heterogeneity can be safely excluded by mathematically testing for it. We will see the mathematical methods in the next few slides. Now, what is a random effect analysis then? If there is a significant heterogeneity, we must assume that the studies are not measuring the same common treatment effect. Each study shows different effects that are normally distributed around true mean, that is, random effects. This assumption gives proportionally greater weight to smaller studies. So this model is susceptible to publication bias and results in wider, less precise confidence intervals. To further understand the difference between fixed and random effects, consider a hypothetical trial where you want to assess the true risk of a beneficial effect when using olanzapine compared to placebo. If true beneficial effect of olanzapine is X, then fixed effects model assumes that individual studies have provided results as x1, x2, x3, etc. True X is simply a mean value. If true beneficial effect of olanzapine is X, then random effects model assumes that the individual studies have provided results such as A, B, M, Y, etc. True X is somewhere in the distribution. How can we assess statistical heterogeneity? We can visually look for statistical heterogeneity in a forest plot and also on other plots used in the meta-analysis such as a Labbé plot and Galbraith plot. We can numerically quantify and assess the significance of statistical heterogeneity using either I-squared statistics or Cochrane's Q test. In this forest plot, see how well the confidence intervals of the individual trials overlap. If the confidence intervals of two studies don't overlap at all, there is likely to be more heterogeneity. This is statistically confirmed by looking at the chi-square values. If p-value is greater than 0.1, there is no significant heterogeneity. We can also check if the chi-square value is smaller than the degree of freedom. Here, the value 0.79 is smaller than 2, so there is no significant heterogeneity. Conversely, if the degree of freedom is smaller, then we can suspect heterogeneity. Look at this plot where the horizontal lines are overlapping a lot less when compared to the previous forest plot. The degree of freedom is 10, much smaller than the chi-square value of 29.8. The p-value of the chi-square test also suggests significant heterogeneity in this case. Some authors also use I-square values to guide the assessment of heterogeneity. As a rule of thumb, if I-square is greater than 50%, we can suspect significant heterogeneity. In this example, I-square value is 0, which is less than 50, so there is no significant heterogeneity. When testing for the presence of significant heterogeneity with chi-square test or I-square statistics, we need to keep in mind that these statistical tests lack power to detect homogeneity in most meta-analyses. So, a more lenient p-value of 0.1 is used for this test rather than the conventional p-value of 0.05. Further, we can only say if significant heterogeneity is present or not based on these tests. We cannot say if the studies are homogeneous. So most researchers prefer conducting both fixed and random effect analysis and report both results in a meta-analysis. Coming back to the line of no effect. In this plot, it represents the value of 1. Relative risk of 1 means there is no difference between the two groups. In other plots, you may see the line of no effect going through the value 0. In this plot, effect size is represented by a mean difference in a continuous score between the two groups. In this case, 0 represents the lack of difference between the two groups. So, if the summary statistics is a risk value, 1 will be the value of no effect. If it is a mean difference, then 0 will be the value of no difference. Risk values that are reported as final point estimates include relative risk and odds ratio. Continuous measures are compared using standardized mean difference. This is also called Cohen's d. Example, when comparing the mean weight of two groups, one receiving olanzapine and the other receiving placebo. Or comparing HAM-D scores of the two groups, one receiving paroxetine and the other receiving clomipramine. Categorical measures are compared using odds ratio or relative risk. For example, when comparing the number of obese individuals in two groups. Obese versus not obese is a categorical comparison. Now it's time to ask yourself a few questions. When would you use fixed effects model? Is it good to have a long diamond lozenge with edges far removed from each other? How will heterogeneity be affected if you add more studies to a meta-analysis? Thank you for choosing SPMM course for your revision.